Hi, everybody, and welcome to today's session. Today is actually supposed to be a lab, but we're converting it to a problem session because we really don't have any lab. We're done with all of the labs. We're done all of the lectures, and this is actually the last scheduled session we're going to have together. I mean, we still have time if you guys need to meet or have a discussion or something like that. Granted, the exam is going to be a Wednesday from today, a week from today, really, okay? So today is Wednesday and next week is Wednesday. So that's when you're going to have the exam. The way it works in here is the following. You will have exactly an hour and a half to do the exam, plus another half an hour for a total of 2 hours to basically do the exam and upload your work. Canvas keeps tab on when you start the exam. So I will know when you're supposed to end it, when you're supposed to finish it. As a matter of fact, if you don't finish it, if you don't submit it, Canvas will submit it on your behalf as basically a blank exam that you did not turn in anything. Now, if you have problems while uploading your work, okay, then what I suggest is that you take pictures of it at least with your phone and email it, okay? Here is the catch too. You have to do that within your time. Let's say, for example, the exam is going to be available at 10 o'clock in the morning, and it's going to expire at 10 p.m. at night. You have this 12-hour window, if you're working during the daytime, to basically do it at night, or if you're working at night to do it during daytime. But here is the thing. Once you start it, you cannot come back to it. So technically, you really should not start the exam unless you know for sure you have at least that 2-hour window to do the exam, answer all of the questions, scan it or take pictures of it and upload it to Canvas or email it, whichever is basically happen to be the case. In other words, I will be checking the time. So I will see when you started the exam and when you submitted it. Any exam submitted after its own last time, that's not going to be accepted. That is item 1. Item 2, the exams are coming from a data bank, basically, of questions. Not 2 exams are the same, meaning if you inquire about somebody's exam, he or she will have different questions, different probably problems, different data, different things to work with. So they will be too busy with their own problems to really give you help with what you need with, okay? So you really have to focus on your own exam. Now the side is for the second midterm. The final is still scheduled to be on campus. The final is still scheduled the week after. Unless I was told otherwise, this is still the case. Does this answer your question? Okay, because we have two big exams coming. Exam 2, which is really midterm 2, if you want to, covering chapters 27, 28, 29, 30, 31, 32. And then a comprehensive exam. The comprehensive exam will be on campus. The second exam will be not on campus. Did I say campus? On campus. So the final will be on campus. The final is everything from chapter 21 to 32. However, the second exam will be on Canvas. Okay, so in other words, there is a window, most likely it's from 10 to 10, about 12-hour window, for you to say, okay, I'm ready for the exam. I don't have anything for the next 2 hours, okay? I'm done with everything. I'm fully rested. I have eaten. I had my coffee ready to go, and I'm ready to do my exam. You click, you enter. At that time, Canvas starts basically your exam. You will get all of the questions. There are 4 questions, okay, to answer. Try to scan through them. They all have the same number of points, but some you might find them easier for you to do than others. So go through all 4 of them and decide, you know, I need to do this one, and this one. Let me think about this one a little more, and then I will have it. It's an open book. So you can look at the pages, you can look at the formulas, you can look at everything that you need, okay? if you start Googling stuff and looking for things online, you're going to be wasting valuable time because you're not going to find much help in there. So it's much better to start on your problems and work with them, do your best with them. Do not forget the units because you're going to lose unnecessary points in there. I give partial credits, meaning don't leave a question and insert. Just start it. Remember the 6 steps that I gave you during the contact when we first met? Apply those, meaning read the problem, understand what the problem is asking, list what is given, what is asked to do, look into the formulas that you're going to need, the things that you know from before and connect it to that. Then go through the solution. Now, justification during exams is not really necessary, but go through the solution step by step. While you're solving it, then at the end, answer the questions and don't forget the units, okay? Now, the other 2 steps, namely justify the steps and also justify your work, basically, and also to have a discussion at the end are not, so basically there are 4 requirements actually for the solving problems. The other 2 do not apply for exams. They do apply for homework and other assignments, but not for exams. So this is something, and you should have a copy of that. If you don't, please let me know. I'll probably also make it available on Canvas just in case you don't have it with you handy. So
it cut off. A copy of what? I'm sorry, Professor. I don't mean to interrupt. A copy of what? Because it cut off for me.
Remember when we met, I gave you, actually I wrote it on the board and I also gave you a piece of paper on how to solve problems.
Okay.
That process, okay?
Okay. I think I remember it. I just don't have the paper no more, I think, to be honest.
Okay, no problem. I will share the steps with you guys on Canvas and try to stick to it, because that way you're going to harness a lot of credit, basically following the method. And even if you get the answer wrong, your steps show me exactly where you went wrong on it. So you get partial credit, at least up to that point. And then if you make a mistake based on a mistake, then you still get a credit, because just because you made the first mistake does not penalize you, because had you get it right, it should not trigger to the next one, and so on and so forth. So that's basically how I work with these things. Okay. SAD, yes. So this online exam is separate from. No, those quizzes are different. So there are 2 sets of quizzes that you guys see. Those are just quizzes. They're actually the intent of those quizzes is just to help you prepare for the exams. Make sense? They're conceptual quizzes. Does this answer your question?
Sorry if you said it, but when is the midterms due?
The midterm is going to be on the same day. When you start it, it's going to be due within 2 hours after you start it.
I mean, like which day? Like, did you
Wednesday, what is Wednesday week from today? The 2nd of June. June 2nd.
Oh, okay, thank you. Thank you.
No problem. No problem. So again, let's clarify everything, and I'm going to follow up with the message, okay, on Canvas. So basically, there is a midterm Wednesday the 2nd, and there is a final. I forgot which day it is, but it's going to be the week after, okay? It's probably a Monday, I think, the Monday after. The final is comprehensive. How to prepare for the final? Make sure you know everything that we did in the class in terms of problems, especially the 2 exams that you're having. Okay? Then you come to the final, which is supposed to be on Monday on campus, okay? Now, if there is a change in the plan, if they tell us, you know what, we can't have you guys on campus, so we're going to revert that to, again, online, and it's going to be on the same day with the same format on how exam 2 is going to happen, okay? So exam 2, again, you'll be given, except the final, you will have more problems, therefore more time, okay? So here is the deal. On Wednesday, the 2nd of June, you will have your second midterm, or the second exam, whichever you call it in here, okay? So it's basically chapters 27 through 32, okay? The focus is going to be on circuits, basically AC circuits, especially the RLC circuit. The focus is going to be on this chapter, chapter 32. And the focus is going to be basically on how to find the magnetic field with Ampere's law. If you remember, there was a problem using Gauss's law from exam 1, where they gave you different surfaces with different charge distributions, and you were supposed to find the flux of the electric field there. Here, you're going to be given currents, and you're supposed to find the circulation of the magnetic field applying Ampere's law. So this is basically stuff that is testable materials for this level in here at this point. Okay, then the final is comprehensive 21 through 27 all the way to 32, and these two exams are independent of the quizzes that you already have on Canvas, which they have a due date. I don't remember exactly where it is right now because I don't have them on top of my head. And also you have I think a lab or something that is due this weekend and stuff like that, okay? Now, if you have missed some work and it's still not graded, that means you didn't get a 0 in it, you are strongly urged to take care of that. Hopefully, don't forget sight of the priority of things. Labs, they weigh heavily, but then in an individual lab, it doesn't really count as much as the global labs. But the exams, because they are fewer, and they weigh a lot, so they have a lot of weight in them, okay? So this is in a nutshell in terms of the plan for everything else. And as I said, you will receive a communication from Canvas detailing all of the things that I was talking about. The key thing for the exams when they are online is that they are timed. It's not like an open-ended, you have all the time in the world. And the uploading time is also factored in. If for some reason you're running into difficulties, I need to know about it immediately, which means I will be monitoring Canvas at that time, during that day, up to 8 p.m. If there is any problem after 8 p.m., it's on your own expense, because there will be no time, actually slightly before that, it's going to be 7:30 p.m. It's going to be on your own expense, because I will not have time to basically react to your request and then communicate it to everybody else if this is a matter that benefits everybody. So if there is an issue, you really need to know, that's why you need to really start on your exam as soon as possible when it's online, okay? So that's basically in a nutshell, everything that I had in mind, and let's get going with the problems in here. Sounds good?
Yep.
Okay, so let me share the screen with you. Let me bring this one closer in here a little. Move this one down. So we're doing problems from chapter 32. And the problems I have in mind are the following. Problem 22, which is really a good problem to start with. 23. And I'm going to put them in the order that I had in mind to do them. Okay, so they probably appear to you out of order, but that's for a reason. So problem 42. And then problem 46. So hopefully you all have piece of paper and you're really ready to rumble, ready to do things, okay? So problem 44 is next. And then after 44 comes problem 35. And problems 51 and 52, which are really one problem, okay? And if you guys feel like it, maybe even problem 37. So these are total 9 problems from this chapter 32 problems, okay? So you guys have a piece of paper ready. You have your pen ready, not just a piece of paper, a bunch of papers. These problems alone are a lot, okay? And you're ready to do this problem. So problem 22, it says a TV broadcasting, public television station KQED in San Francisco broadcast signal radio at a power of, so they gave us the power now to being 777 kilowatt. Okay, I already Googled the stations in the area in here. So I have an idea of how much power each station in here broadcasts. Channel 5, I don't know exactly what they call it in here, KTLA, I think. Channel 5 broadcasts 1,000 kilowatts. That's their power. And it's the strongest signal that is broadcast in our area. There is actually other channels, they're like 100 kilowatts, 50 kilowatts, and some of the smaller stations like 3 kilowatts. So this number is actually a high number. With the exception of channel 5, all of the other channels are around 100 kilowatts, okay? So the fact that this channel in San Francisco is 777 kilowatts, this is actually a very strong signal from this broadcast, from this station. So if there is a problem like this one, you probably are going to get a random station in there in the mix, and you might not be receiving its power. You might get actually the electric field for it, or the magnetic field, and you're going to infer the power from it. So that is basically something that you need to be watchful for. Assume that the wave spreads out uniformly into a hemisphere above the ground at a 5-kilometer house. So basically here is the station broadcasting its signal. And there is a house in here, okay? And the distance between them is 5 kilometers, 3 miles, okay? What average pressure does this wave exert on a totally reflecting surface? So we want to find the pressure P, okay? So the first thing we need to do is find the pointing vector S. Here is the deal. The intensity of the wave, which is the power divided by the area, this is actually the average of pointing vector. So the intensity and pointing vector are the same quantity, okay? That is how Mr. Pointing actually defined the pointing vector in such a way to get the definition for the intensity. So in other words, once you find I, which is the power.
You look good. Good job.
Sarah, do you have a question?
No, sorry. My brother just walked in.
Okay.
Hello, baby brother.
Can we turn off the microphone then?
Huh?
Can you turn off your microphone then?
Yes, sorry.
Okay, no problem. Anyway, so once you find the intensity, then you can find the pressure at this point. Okay, so remember what we found. So this is a totally reflecting surface. It is what we found in lecture, if you guys remember. So let me go back to the notes from the lecture when we found the pressure. So this is the sample of the pressure, the symbol for the pressure P. This is an absorbing material, it's S over C. But for a totally reflecting material, it's 2S over C. Since this is a reflecting material, we're going to use the 2S over C, but we don't have the S, so we have actually the I, which is the same thing. As a matter of fact, during the lecture, I remember we made the point that the I is the same as the pointing vector, okay? Pressure divided by A, it turns out to be the same thing as, so let's do this, take advantage of these things, okay? So since we have the power, so they gave us the power, and it's an average power, so they don't give you an instantaneous value for the power. So when they said that the power is 777 kilowatts, that is actually the average power. Because the power itself, it goes up and down, but on average, it's this much, okay? Because it's fluctuating signal, okay? So it's broadcasting with this much signal, and once it hits in here, and there is a reflecting, what is the average density? No, what is the first question? A. What average pressure does this wave exert on a totally reflecting surface? So in this case, the pressure, P, is going to be basically 2 times I divided by the area A, divided by the speed of light, C, okay? That is a formula that we need to use. However, the intensity is 2 times the power divided by the area and speed of light. So that's all there is to it in this case. So we have an answer for question A. So all I have to do now is plug in the number. So the pressure will be 2 times 777 kilowatts That's what that means, 10 to the power 3 watts, divided by the speed of light, which is 3 times 10 to the power 8, 300 million meters per second. And the area in this case is, okay, we need to know the area. Here is the area. It's this sphere of radius 5 kilometers. So the area should be 4 pi r squared. This is the area of a sphere. Okay, so if we have that, we plug it into here, and it's 4 pi times the 5 kilometers, which is 5 times 10 to the power 3 squared. So now it's a matter just of plugging the numbers and finding the actual pressure. It's going to be in Pascal, because this is a pressure. Everything is in SI, so everything is going to be in Pascal. So let me plug in the numbers and put it in my calculator. By now, I think that you guys are doing the same thing. Okay, so one of the 10 power 3s is going to cancel with this one. So I'm going to put this 10 to the power 3 in here out of the outside, and it's going to be 10 to the power 3. And then this number becomes 25. And 4 times 25 is actually 100. And so we'll have 10 to the power 3 and 10 to the power 2. That's 10 to the power 5 and 10 to the power 8. So it's going to be already 10 to the negative 13. Okay. Then I have 2 times 777 divided by 3, and that's it. Because, 3 pi, I'm sorry. What am I talking about? 3 pi is 10. So it's going to be 10 to the negative 14, or we'll have to work out these details in here to put it in scientific notation, because 777 is too big of a number, okay? So unless you put 7.77 times 10 to the negative 11, then that's going to work. So let's do the numbers in here. 2 times 777 divided by, open parentheses, 3 times pi. Okay, it's 164.8 or 165. So I'm going to write it as 1.65 times 10 to the negative 11 Pascal. Okay, very tiny pressure. Okay, the atmospheric pressure that you and I are sitting under right now is about 100,000 Pascal, just to give you an idea. Okay, so this is extremely small pressure. Okay, part B, what are the amplitude of the electric and magnetic field of the wave? Since we have I, and I is actually the average Poynting vector. And Poynting vector, if you guys remember from lecture, is equal to, first of all, the contribution from the, I'm sorry, we have the cross product of E times B divided by mu naught, basically, okay? It's a vector, but E and B are perpendicular, so that the sine of the angle between them is sine of 90 degrees and sine of 90 degrees is 1. So in magnitude, it's just these two numbers, okay? And E, if you remember, or B, if you remember, is equal to 1 over C times B is 1 over C times E. So it's an E squared divided by C, okay? And C, if you remember, is equal to the 1 over square root of mu naught epsilon naught. So all of these numbers are from the lecture. So I could rework these numbers in here, and I will find some square root of this, and that, but I'm really wanting this number, E squared, okay? But I need to average this quantity. So E itself is a cosine or a sine. E itself is some E amplitude times a cosine of some kx or kz or something minus omega t. When I square it, it's going to be E squared equal to E naught squared times the cosine squared. When I average this quantity, it becomes just like what we did. This quantity is constant, so it has no average. And the average of a cosine squared already, if you remember from chapter 31, the average of a cosine squared or the average of a sine squared is exactly 1/2. So this is just 1/2. So if I plug in the number in here, this S bar, which becomes just I then becomes, I pull a half from the averaging of a cosine squared. So the formula really should be I for the intensity, which is the average of the Poynting vector, should be then equal to 1/2 times the maximum E. So it's going to be the amplitude E naught squared divided by 2 times the mu naught times C. Okay, this is one way of writing it down. Or if you wish, you could play around with this C and cancel C and write it in the numerator and have an epsilon naught instead. Remember that you can, there is another way of rewriting this expression, but in terms of epsilon naught. I prefer to write it in mu naught. It should give me the same thing. From here, I should be able to find the value of E naught. E naught is equal to the square root of 2 times mu naught times C times I. And I, if you remember from this problem, is P over A. It's 777 kilowatts over the area. So this will be simply equal to square root of 2 times mu naught times C times the power over the area. Let's plug in the numbers. Okay, the strength of the electric field in that region, and see if this really is going to cause damage in your skin so that it have a virus in your blood system, or it's going to cause corona, or it's going to cause cancer. Because there's a lot of rumors going around that corona now is related to this new signal standard for telecommunication. Let's see how much strength of the electric field we're going to get from this station. So E naught is going to be square root of 2 times 4 pi times 10 to the negative 7. This is the value of mu naught, by the way, times C, which is 3 times 10 to the power 8, times the power, which is 777 times 10 to the power 3, divided by the area, and the area is 5 times, or 25 if you wish, times 10 to the power 6. I already squared 5 kilo times 4 pi. I already squared the r cubed in here, r squared in here, okay? R is 5 times 10 to the power 3 meters. So when I square, it's going to be 25 10 to the power 6. 10 to the power 6 and 10 to the power 8 is 2. Okay, 2 and 5 is 10 to the power 2, and this number is going to be 10 to the power 5 with 10 to the negative 7. So this number is going to be 10 to the negative 2, and 10 to the negative 2 will just change the decimal point in here. So what I have at the end of the day is the following. First of all, the 4 pi and the 4 pi cancel. Okay, so what I have in this case is E naught, or the square root of. It's a good idea to always try to simplify your input in the calculator to minimize the number of mistakes you make. Because if you have to enter a lot of powers and a lot of digits in a calculator, there is a chance where you are going to have a lot of mistakes. Okay, but again, you're supposed to check my work. Okay, don't take my work for as a truth in here. 2 times 3 is 6. 7.77. I already took care of that power in here with the decimal point, divided by 25. Okay, so 6 times 7, 6 times 8 is about 48, divided by 25 is about the square root of 2. Okay, so that's what I'm looking at. Square root of 2 is roughly 1.4, 1.5. At the end is going to be a voltmeter. That's the unit for the electric field. So let me write it down. Square root of, open parentheses, 6 times 7.777. Unless, did I miss a point in here? No, everything looks good. Divided by 25, and close the parentheses and hit enter. So it's giving me 1.36 or 1.37 actually. Volt per meter. This is a very tiny electric field. It's not going to budge anything. It's not going to move anything. Okay. Your eyes are not going to react to this much of the strength of the signal here. Okay. This is a very tiny electric field. As a matter of fact, we're supposed to find the strength of the magnetic field. The strength of the magnetic field B naught is supposed to be equal to E naught over C. And this is also another result that we found in the lecture. So it's going to be 1.37 divided by 3 times 10 to the power 8. And it's going to be in Tesla, of course. So we take this number. Come on. This calculator is not responding. I hate it when it doesn't respond to me. Okay, divided by 3. All I need to do. So it's going to be 0.45 or 4.55 nanotesla. Very tiny magnetic field, okay? Because you have 10 to the negative 8, and you have another decimal point that was in here, so I moved that one, it became 10 to the negative 9 Tesla. So this is a very tiny magnetic field. Usually the magnetic field is very small due to the EM waves. This is because of the C in the denominator always. So most of the time you're worried only about the electric field because the magnetic field is extremely small, okay? So we answered that part. What is the average density of the energy this wave carries? U. So we need to find U. The energy density that this one carries. Okay. Again, U, average. You have to average this quantity. Remember, during the lecture, let me go back through the lecture. When we were finding U by itself, did we calculate it in here or? No, it's in here. So it's 1/2 of epsilon naught times E squared plus B squared over 2 mu naught. But E itself is C times B. So if I work these numbers, it's going to be EB divided by mu naught C. That's basically what it is. It's just basically the S vector divided by C. So that's basically I over C. Okay? Because when you average this quantity, it's going to be the average of S over C, and the average of S is just the I. So this is going to be actually I over C. Okay? And the value for that is going to be basically half of this number, whatever that number is, okay? So it's going to be a very tiny number in joules, okay? Let me check in here to make sure I didn't give you the wrong formula. Most of the time I end up, no, this is the power, I'm sorry. So it's going to be EB over mu naught C, yeah, times this is U, okay? Yeah, that's the energy density, that's correct. So it's S over C, but when averaging it, it's going to be I over C. And I over C, we have the I again, which is the power divided by A times C. And this is going to be, we did this number already when we did when we did the perfectly reflecting, okay? Had this been not a perfectly reflecting, this number would be 1. Had been perfectly absorbing, this number will be 1. So the actual number is going to be 1.65 divided by 2. It's going to be 0.83, roughly. So it's going to be 0.83 or 8.3 times 10 to the negative 12, actually, joules per cubic meter. Okay, verify these numbers, check them, okay? So don't rely on my stuff in here, okay? Part D. For the energy density in part C, what percentage is due to the electric field and what percentage is due to the magnetic field? This question has nothing to do with this problem. Let me tell you why. When we did the lecture, we found the electric field from the magnetic field contributes by a factor of 1. And in the same time, the energy from the magnetic field contributes by an amount of 1, because this number is actually 1. Mu naught epsilon naught is actually 1 over C squared times C squared is going to be 1. So both of them contribute the same. So this question really is part of the lecture, and the answer to it, both of them contribute the same thing. And the point being we're trying to say in here is that 50% is from E and 50% is from B. In other words, although B is so small in magnitude, and it does not have really direct effect on charges moving in it because it's so tiny. So your eyes are more sensitive to the electric field and they work more with the electric field. But when it comes to energy, both of them have the same thing. In other words, both the electric field and the magnetic field cannot survive without the other. Because the entire energy of the wave is the sum of both of them, and they come in with equal contributions. So that's why this is important. In other words, it's like the mass spring system, actually. If I take a mass spring system, I have to have a mass and I have to have a spring. And the energy sometimes is kinetic, sometimes is potential, and this is the total energy of the mass spring system. This is exactly what this means, is that the total energy is coming 50-50 from both the electric field and the magnetic field. And when we explored it in class, when we added both of them, we found that both of them have the same contribution, because this number is the same as this number, no matter how you write it down, okay? As a matter of fact, and I did not do this, so actually we could have done this, we can write it as 1/2 of epsilon times C times E times B. We could have done that, okay? And it's the same thing, where B is just E over C. So we could have written it that way, okay? So it's the same expression in there. So this is problem 22. Again, the purpose that we're meeting during lab so that we can do this problem, so that we can move at our own pace. And if you guys have any questions, please do not hesitate to ask them if this is the time or not. So this is the time when you're supposed to do these things. And you're supposed to be numbers on your own too. Somebody has a question?
Yeah, I do. Just quick question right there with the where you canceled out. Like, what did you cancel out exactly? Right there. Yeah, right here.
The 4π and the 4π.
Okay.
And the powers.
So like the 3 and the 6.
Okay, hold on. I have 10 to the power 6 and 10 to the power 8. So that gives me 10 to the power 2, 10 to the power 6 is gone, and 10 to the power 8 is gone. I have 10 to the power 2 and 10 to the power 5. That's 10 to the power, 10 to the power 2 and 10 to the power 3. That's 10 to the power 5. And 10 to the negative 7. So that's going to leave me with 10 to the negative 2, correct?
Yes, correct.
Because I have +5 and -7, that's -2. And then I cancel the last 2 by moving the decimal point in here in the 777 by writing in 7.77.
Okay, so that's where the 7.7 came from. Okay.
Yes. So when all the dust settles, plus of course the 4π is cancelled. This is part of the area of a sphere, 4π r squared, and this is actually the value of mu naught. Mu naught is always 4π 10 to the negative 7 SI, of course. Okay. So the 4π is cancelled. So when all the dust settles, I have 2 times 3, which is 6, times 7.77 divided by 25.
Okay. Thank you.
Okay. No problem. This is actually a good thing to practice on your own too, so that you save time instead of punching the wrong numbers, and you find out some ridiculous numbers in here that don't make sense to you. You're looking at it. Why is the electric field? Didn't he say that the electric field is supposed to be a small number? And now I'm finding a huge electric field that probably maybe the person sitting in home will be electrocuted just by watching TV. I mean, the signal, even if you don't turn on the TV on, okay, it's going to be a problem because tremendous electric field that is going to be there. So you should be seeing sparks every which way. And you're not seeing that. So yeah, it has to make sense to you, okay? So no problem. It's a good idea to practice playing around with numbers so that when you punch in the numbers, you get good enough answers here, okay? So this is problem 22. Let's take on problem 23. Problem 23, I was really hesitant to do it, but then I decided it's a good problem also to do that. And problem 23 has to do with the, they tell you always never point your laser to an airplane because lasers are actually, albeit, I mean, they're kind of, they seem to carry very little energy, but they could be very damaging. Right now, you're not even looking at it. And if I turn my hand to you, well, it's going to be really, really high intensity. So I'm putting it at an angle. So they're really dangerous things and carry with them a tremendous amount of energy too with them. So the red one in here is less intense than the green one. The point being in here is you have to have an understanding of what's going on in here. So problem 23. If the eye receives an average intensity of 10 to the power 2 watts per meter squared, damage to the retina can occur. So you don't want anything more than 10 to the power 2 watts per meter squared, period. It's not much really, 100 watts per meter squared. And because these things, they focus energy in a single point, because of the width, they could bring that to you. Remember, the width of the beam is so small. So although the intensity is not a lot of wattage coming off of it, but it's all focused in a single point. So they could cause damage to the eye in that point. So damage to the retina can occur. This quantity is called the damage threshold of the retina. So again, this is an experimental thing. So probably you bring a bunch of mice and you start playing around with them until they go blind. And then at the end, you scale it up and you say, this is what happened to a human, because you're not supposed to do this experiment on a human, okay? Unless somebody owes you money or something. Okay? Don't do it even if he owes you money, okay? It's a criminal. Okay? So what is the largest average power in milliwatt that a laser of 1.5 millimeter in diameter can have and still be considered safe to be viewed on? So imagine, what is this one? Which color is this one? This is the red. Imagine this one has a width where it is, where it's focused, not to the entire thing, okay? Not where it's about 1.5 millimeter in diameter, okay? So D is equal to 1.5 millimeter. Okay, that means the radius R is 0.75 millimeters. So tiny. Okay. So how much power would it be considered safe? Okay. And they tell you, most lasers, they tell you how much power they have. Okay. So we know that the intensity is equal to the power over the area. From here, I'm going to find the power to being thus the intensity times the area. And we're in business. We have everything. We have. Now, the only problem with this one is that this is the area. It's pi r squared, okay? It's going on a flat surface, okay? So it goes to the retina on that area and basically start to do damage on it, okay? So it doesn't matter how long it's exposed, okay? Even if for a fraction of a second, it's really dangerous. Do not play with these things, okay? They are very, very dangerous. Do not point them on somebody, okay? They are very dangerous, okay? Don't point them on dogs either. So please don't do that, okay? If you want to have fun, probably play them with them and point them to somebody who owes you money or somebody who did you wrong or something like. Don't even do that. Are you guys having fun or not? Or am I the only one who seems to be in the mood for laughter today? Okay, anyway, so let's do this. We have the intensity. We need 10 to the power 2 at most before it becomes dangerous. And the area is pi times 0.75, 10 to the negative 3 squared. Okay? So don't forget that you have to square the, and I already converted into meters. So again, I have 10 to the negative 6 in here, coming from this number. And I have to play around with these numbers to see what I'm going to get in here. So I have 100, times pi, times 0.75 squared. Okay, so why is this not? Times pi times 0.75 squared. Sometimes this calculation. So it's giving me 176 times 76.7. So it's going to be 177 really, times 10 to the negative 6 or 1.7. 7 times 10 to the negative 4 watts. That doesn't sound much, does it? So if a laser beam has more than this power, okay, you are in trouble. 0.177 milliwatts. It's a big limit in here. So if you're using a laser beam that have a little more than this power, it could be damaging to the retina, to the eye. Okay. So what are the maximum values of the electric and magnetic field for the beam in part A? So now,
quick question here, if that's okay.
Yes.
Why is the area here just pi times the radius squared instead of like 4 pi r squared?
That's a very good question. Let's make this distinction, okay, because sometimes it's confusing. For the first problem, I have an energy that spreads throughout a sphere, okay? So this is a three-dimensional sphere, correct? So if I come in here with an antenna and use it in here, this energy now spread throughout the sphere, and all I'm collecting is part of a sphere. Make sense?
Yeah, that part makes sense for sure.
So, like this. But in here, what I have in here is that I have this intensity coming on this basically shape in here, and it's like a cylinder on the beam. And when it comes in here, it's going to hit that area. So I'm not worried about it spreading around. So for a laser beam, it's focused, and when it hits this area of diameter d or radius r, so the area in this case is pi r squared. That is the area of a sphere. So the area of a circle in this case is pi times the radius squared. The area of a sphere where I was concerned, because all of the energy was gone every which way, and only I'm worried about this part of it in here. So the other ones are just basically wasted. So my antenna is in this point in here. So this one spreads on the entire sphere of radius r, and the area of a sphere, it's like the onion basically. When you take the outer layer shell of the onion, that is the area, 4 pi r squared. Okay. Whereas this area is just basically, as the beam coming in here, it's going to hit this portion of the retina, which is a circle actually of radius r. Does this answer the question?
Yeah, for sure. It makes more sense.
Okay, very good. Very good. So in this case, that is the value in here that we have for this question. So now we want to find the electric field, okay, associated with this wave. Remember, we have an intensity that is given in here, I, and we just found how I is related to the electric field. Where is the expression that we have in here? This is the expression that we need to use. So E naught is going to be square root of 2 mu naught times C times I. And we have I now. So we have everything now. C is 3 times 10 to the power 8, and mu naught is just 4 pi 10 to the negative 7. From here, we're going to find the electric field, E naught, to be square root of 2 times mu naught times C times I. We have everything for this problem now. So because we already started with I, so let me remind you, the I is pointing vector, the average pointing vector, okay? So all I have to do now is plug in the numbers. This is square root of 2 times 4 pi 10 to the negative 7. That is the value of mu naught, actually, times 3 times 10 to the power 8. That is C, times I, and I is 10 to the power 2. Watts per meter squared, already given to us. Again, negative 8 and positive, negative 7 and positive 8, that's positive 1. So all I'm doing now is 4 times 3 times, or 2 times 3 times 4, that's 24. Pi times 1,000. So this will become equal to 24 pi times 1,000 under the square root. So the electric field now is stronger than before. So let's see how that is going to be. Square root of, open parentheses, of 24 pi times 10 to the power 3. It's 274.58. Okay, so I'm rounding it at 275 voltmeter. Remember, sometimes we use a Newton Coulomb. That's how we define the electric field the first time around. But then after that, we use the volt over meter as a standard unit for the electric field. Okay. So it's a good strong magnetic electric field, because now we're dealing with a big strong signal. Okay. Laser beam focuses basically the energy. That's why it's really bigger now. So B naught is E naught over C. Okay. And E naught is 275 divided by 3 times 10 to the power 8. If I'm running out of time, I know 275 is roughly 300. And 300 cancel this number to give me 6. And the 3 cancels the 3 is going to be just 1. So it's going to be 10 to the negative 6 Tesla. Obviously, I'm not running out of time, so I'm going to do 275 over 3 times 10 to the power 8. And it should be roughly, it's going to be slightly less than 10 to the negative 6 Tesla. So as a matter of fact, let's do this. And use the actual number divided by, open parentheses, 3 times 10 to the power 8. Close the parentheses. So according to this number in here, it's 9 times 10 to the negative 9.15 times 10 to the negative 7 Tesla. These two numbers are very close from one another, because 9 times 10 to the negative 7 is, this is roughly 0.9. 10 to the negative 6. That's exactly my estimate earlier, okay? So it's very close from that. So again, when you're doing numbers, pay attention to these things in here. Sometimes you punch in the wrong number and you get some nonsense stuff in there and you, oh man, this is, for some reason now I have a strong magnetic field, okay? So when you're running and you don't have a calculator, 275 is roughly 300. Divided by 3, that's about 100. Divided by 10 to the power 8, that's 10 to the negative 6. Okay, so it's again micro Tesla. So it's 0.915 micro Tesla. Okay, very tiny magnetic field. The magnetic field usually is a small number. Okay. C. How much energy would the beam in part A deliver per second to the retina? Now we need to find the energy, du over dt, the power basically, du over dt. Okay, that is actually the power, okay? And the power is already given. This is how much it is, okay? So it's 0.177 milliwatts. How much energy would the energy deliver per second? Energy delivered per second, that's the power. So you really don't need to do anything about this question. It's already done for you. You did it in here. Okay? So that is the answer to that. How many sig figs do we have in this problem? Just to make sure that. There are 2 sig figs. I'm keeping 3, so this should be 0.18, okay? Milliwatt. And this should be 0.92 micro Tesla. So everything is actually 2 sig figs, okay? So this would be 280 voltmeter, and so on and so forth, okay? So please fix those things in there, okay? Accordingly. Express the damage threshold in watt per centimeter squared. Okay, again, now we want it in watts per centimeter squared, because the retina is not that big, really. It's very small. It's a few centimeters squared. So the intensity actually is equal to 10 to the power 2 watts per meter squared, and the meter squared is 10 to the power 2 actually squared in centimeter squared. So this is watt, and 10 to the power 2 squared. Cancel one of this with that, so it's going to be 0.01 watts per centimeter squared. So this centimeter squared. This problem is kind of also an appetizer problem, so that you guys can see how you manipulate the numbers and understand how things work and things like that. So this is problem 23. The next problem is a big problem. And that is actually 23, this chapter 32 mixed with chapter 31, okay? So let me look at this problem, and this problem is a very big problem. So please focus on this problem. Problem 42. So if you guys have the book, please go jump to problem 42. So what you have in here, you have an antenna. Think of your cell phone, and I don't know where my cell phone is. Think of your cell phone, and on the back of it, there is an antenna that is wrapped around so that when the signal is coming, it's going to excite it. So let's draw this picture first of all. So we have a bunch of loops in here. A bunch of turns, I should say. I'm gonna draw probably only 3. Okay. So it's wrapped around several times to go around it. And here I have an R. And in here I have a capacitor. And in here I have an ammeter. Usually it's a galvanometer actually, because the currents usually are not that strong. And I'm supposed to find the current in here that is going to flow through this one. So what they give us in here, the width is A, and the height is A of this turns. So it's actually square shape in here. So the area is A squared. Okay, that's one thing. It has n turns. Okay, so each one of them is going to be multiplied by n to get the total. That leads to a resistor R. So R is given, C is given, the capacitor, a plane wave. Okay, we have to talk about the axis, okay? So this is the y-axis. This is the x-axis. And this is the z-axis. Okay. Then you have a plane wave where the electric field is along the y direction, but varying in the z direction. So the electric field E as a vector has a magnitude E max, which I'm going to write it E naught because I really don't like to write that MAX all the way and then carrying it every which way. Cosine KZ minus omega t, and this one is actually in the j hat direction. The magnetic field then cannot be in the z direction. The magnetic field can only be in the x direction. So B immediately has to be, because B is perpendicular to E and perpendicular to the direction of motion, direction of the wave. So B must be B naught, and it's the same temporal and spatial dependence as the electric field. That's what we saw in lecture. A cosine kz minus omega t, but this one must be in the I hat direction, where B naught is E naught over C. Okay? So we don't have to do a lot, we don't go through the lecture and do the derivation again and solve Maxwell's equations. We're going to take advantage of what we did in lecture. The electric field and the magnetic field are always perpendicular to one another, and they're perpendicular to the direction of motion, direction of the wave. The wave, how do I know which direction? It's in direction Z, because they gave me this one in the electric field. So the wave is moving along the Z axis. The electric field is actually polarized along the y direction. The magnetic field then must be along the x direction. And both of them have to be in phase. So there is no phase difference. And both of them have to have the same dependency. This is B naught, and this is E naught. This is the maximum electric field. This is the maximum magnetic field, in such a way that the ratio of the electric field maximum divided by C is the same as B naught. This is what we have found in lecture. So they didn't tell us these things. We inferred based on what we know. So this is the stuff I'm telling you in here. So if you're given the expression for E in this form, you know immediately it's moving in the Z direction. So E cannot be in the Z direction, end of the story, period. Okay? And so is B for that matter. Both of them, in other words, EZ is equal to 0 and BZ is equal to 0 from here, from this thing. Had they put an X in here, then I can tell you EX is 0 and BX is 0. Okay? So in this case, there is no electric field along the Z direction and there is no magnetic field along the Z direction. Now, they polarize this beam so that it's the electric field is along the Y direction. If the electric field along the Y direction, then the magnetic field must be perpendicular to it, and it has to be along the X direction. Because it cannot have a Z component because it's traveling in the Z direction, and it cannot have a Y component because the electric field is in the Y direction. Does this argument make sense to you guys? They didn't give us this. We deduced it. From what we know in lecture. Okay? Again, let me make the argument for it. They gave us axes in here. Forget about the rest of the circuit now, because you have to focus on the beam first. You have to focus on the electromagnetic waves that is hitting this entire circuit in here. They say specifically that it's traveling actually in the Z direction. Okay? They say a plane electromagnetic wave with an electric field propagates in the plus Z direction. So it's moving in the positive Z direction. So we know then and there, at that point, the electric field and the magnetic field have no components in the Z direction. Now, the electric field could have components on the X direction, Y direction, or a combination of both of them. The magnetic field could have then, in that case, a component in the Y direction and the X direction, or composition of them in such a way that both of them, they stay perpendicular still. So the electric field and the magnetic field stay perpendicular at all times. Now, since they specifically stated that the electric field is along the J-hat direction, then I have no choice but to take the magnetic field along the X direction with the same pace and a magnitude that satisfies this condition based on what we saw in lecture. Does this make sense to you guys? Okay, very good. So we know what the magnetic field is. So let's see what the questions are. The origin is shown in the picture. So the origin is just in the middle of this loops in here, just smack in the middle. So the coordinates for the middle here 0, 0. So the corners in here are all of them have A over 2 and A over 2 and combination of these things in here. Okay, they're on the plane. What is the magnetic flux through the coil in the direction of the X-axis? So we have the area, which is along the area of this whole thing is along the X-axis. So this is the area of this loop, okay? When you take a loop, it's the area pointing along the X direction. So in this case, if I take a patch of an area of width this is this is Y direction, so this is dy and dz, okay? So the flux in that area, d phi, of the magnetic field is going to be just the product of the two. The magnetic field times the area, which I took to be dz times dy. Okay, I'm sorry. Yeah, because B is along the X direction and the area is along the X direction. So I have a cosine of 0 between them. Remember, this one is actually supposed to be B times dA. Okay? But both of them are in the X direction. So there is a cosine of 0 degrees between them. So that's why I'm not worried about that, okay? So dy dz is an area pointing in the X direction. Dy dx is an area pointing in the Z direction. dx dz is an area pointing in the Y direction. So you have to pay attention here. So if they give you dy dx, that is actually in the Z direction. Or k, what do we call it? what is the symbol for the z hat direction? Is it k hat? I, j, k? Yeah, k hat direction. And then in the dx, dx, dz, that is actually an area in the j hat direction. And like we have it now in here, dy, dz, this is actually in the I hat direction, okay? Because the y and z plane pointing in the x direction, the third direction, which is the j hat, I hat direction. So, and the B field is actually along the I hat direction. So that's why they have a cosine of 0, which is 1 in here. Now, when the area varies, so y changes from negative a over 2, because remember the origin right smack in the middle, to a over 2, and z changes also from negative a over 2 to a over 2. The magnetic field B has B naught times cosine of kz minus omega t dy dz. This depends on z. So when I integrate over a, all I'm going to do is pull up an a over 2 minus an a over 2, so it's going to be an a. So in other words, I could have taken this area instead of this area in here. I could have taken this area. Let me choose a different color. We could have taken this area of length a and width dz in vary z from negative a over 2 to positive a over 2. I'm going to find the same result. So this is the area that we should have taken. In that case, because the magnetic field does not depend on the y direction. It depends only on the z direction. As you can clearly see in here, it has a kz in it. So when we integrate, when we sum, that is the only variable that's going to mess up things for us. Having said that, let's find now the flux of the magnetic field now. The flux of the magnetic field is going to be, first of all, I have a B naught times A from the this summation, or times this A here. So it's B naught times A times the integral from negative A over 2 to positive A over 2 of a cosine of kz minus omega t integrated over z. Okay? When we integrate over z, this is just a constant. So it's not going to matter really. So in other words, I'm going to make the following change of variable if you like. I'm going to call u equals to kz minus omega t, which means that du is equal to k dz. So I'm going to pull for dz, I'm going to just write du over k, and I'm going to be left with integrating a cosine of u. Okay? And the integral of a cosine of u is clearly sine of u, because the derivative of cosine is just a sine. So the integration in here will have a 1 over k, because it's coming from this expression for the dz. So it's going to have 1 over k times sine of u, and sine of u is kz minus omega t. And the boundaries of integration are actually from negative a over 2 to positive a over 2. And what is that? So times b naught a, and this is equal to phi b. Okay. So I have to be careful in here because this is the boundaries of integration are for z. In other words, this is the expression that I'm going to be left with. Phi b is equal to b naught a over k times sine of ka over 2 minus omega t minus sine of minus kz, ka over 2 minus omega t. So I plugged in the value in here in the upper limit and the lower limit. Note the following. The sine function is an odd function. Sine of negative x is the same as negative sine of x. So this will become a negative sine of ka over 2 plus omega t. But don't forget I have a negative already. So this will become a positive. So what we ended up with is the following thing in here when we do the algebra. Phi b is equal to b naught a over k times, again, open parentheses, sine of ka over 2 minus omega t plus sine of ka over 2 plus omega t. They gave you a trig identity. If you look at the book, it says that, note that sine of a plus b plus sine of A minus B is equal to 2 times of sine of A times sine of B. So basically they tell you, note that if I give you sine of alpha plus beta plus sine of alpha minus beta, they should not have gave you A and B, because you already have a B for the magnetic field, and that would have confused the thing. So that's why I'm switching it to alpha and beta is equal to 2 times sine of alpha cosine of beta. Okay? Cosine of beta is the one that flips the signs. Alpha does not change signs. So in other words, this is exactly the situation here, except alpha is Ka over 2, and beta is omega t. So having said that, now we have a value for phi b, for the flux of the magnetic field. The flux of the magnetic field then is going to be 2 times B naught A divided by K times a sine of Ka over 2 times a cosine of omega t. So this is the flux of the magnetic field. Does this make sense to you guys? If you find this too much, please go through the steps step by step, please. Okay, thank you. Okay, so this is a time varying flux. It changes with time. The phi is not constant. And when phi is not constant, there is an EMF per Faraday's law. The EMF is going to be equal to minus d phi b over dt. Since this flux is not fixed in time, because the wave itself is oscillating, it's time dependent. So when you have an antenna, the only reason why you have an induced current in the circuit is because of that. It's because of the fact that the EM wave itself is time dependent. It comes as a function of time. Therefore, the flux that it's going to induce is going to be time dependent. So there will be current now running through the circuit, and that is how antennas work. So there is an antenna sitting in here, minding its own business. An EM wave comes in, hit it. So this EM wave will have a time varying flux in that region. So this will induce an EMF that will have a current running through it, through the circuit. So now if I tune this has an inductance L, by the way. They tell you also that it has an inductance L. So they gave you an inductance L for it. So now I have an LRC circuit that is being driven by an external EMF, and this EMF is coming from this expression. So basically we're back to chapter 31 at this point. So let's see here now what we have. What is the EMF generated by the coil? Well, in this case, all I have to do is take the derivative. The derivative of cosine is a negative sign, but I have a negative in here. So this is going to take care of the negative, and I will put another omega in here. So it's going to be equal to 2 B naught A over K. And then here I will have an omega, because when I take the derivative of a cosine, it's going to put an omega in here. And this will become sine of Ka over 2 sine of omega t. So this is the EMF. This is an oscillating circuit now. So this is the EMF that I have in that circuit, okay? This is the amplitude of the EMF. This is actually the whole amplitude of the EMF. And this is the time varying part of it, okay? And now remember that omega is equal to KV, or omega is equal to KC. So this ratio omega over C, omega over K is actually the speed of light. So I can write this EMF as simply equal to 2 B naught AC times the sine of Ka over 2 times sine of omega t. If this signal is expected to be any signal that is actually how should I say it? An oscillating signal. This is basically the coming from an EM wave. This is the case for it. Now there is another expression here. I know B naught times C. C is actually the electric field. So this EMF is actually equal to 2 times the electric field max times A times the sine of Ka over 2 times the sine of omega t. So there is another way of rewriting this expression, whether with the electric field or the magnetic field. Since they gave us the electric field, so we really technically should write it in terms of the electric field. What did I know? Did I have a sign in here somehow? Yeah, that's good. Everything is fine. So everything looks good. Okay. So this is now expressed in terms of the electric field, what was given to us, because we know that B naught times C is equal to E naught, the strength of the electric field that was given to us. Okay. The electromagnetic part C, the EM wave has a frequency F for 4 megahertz. So they gave us the frequency F to being 4 megahertz. And also the intensity I is equal to 100 watts per meter squared, okay? The coil has an N equal to 50. Oh, did I forget to multiply this by N? I think I did. I'm sorry, but this is not the full picture. Where is the flux in here? I calculated it only for a single area, but I have N of those, okay? So this is the flux over just a single area, but I have N of this, so I need to multiply this by N, So everywhere you see this answer, you have to multiply it by N. So the flux is actually, there is an N in here, because there are N of them. They're acting like batteries in series, really. So there is an N everywhere in here. I thought it's only one. Basically, I took as if it's only one, and it's not. So there is N everywhere. Please fix this thing in here. Okay. So there are N turns. There's 50 turns in this problem here. Okay. And the side A is 10 centimeters. Okay. 10 to the negative 1 meters. And the inductance L is 78 microhenry. Okay. And the resistance R is 100 ohms. What value of the capacitance C results in the resonance frequency of the RLC circuit? Here is the deal. If you want to build an antenna, it's better be tuned to the broadcasting station for you to maximize the current to its maximum. Okay. Otherwise, you don't have really that much maximum current in the signal. So in order to really take advantage of it, you have to have it in sync. That means this frequency of 4 megahertz, namely omega naught of the circuit, must be equal to 1 over square root of LC, and omega naught must be 2 pi f, where the f is what's given to us. Since we have L, we can find from here, so this is the condition of resonance. Okay, that's how antennas work. They work at resonance, because otherwise, what's the point in here? That's the maximum signal. Remember from the curve that we did for the resonance, that is where it's peaked. So you want that. So in this case, it's going to give me C equals to L times 4 times 2 pi f squared. If I sub for all of them, I find the capacitance needed to be in sync with the signal. So in other words, imagine you're playing with the capacitance and adjusting the capacitance accordingly, which capacitance will give me resonance. And that's exactly how all tuning devices work. You change the area of the capacitance until you are in sync. So the dial that you have on the old radios, actually not the digital ones, they change the capacitance. Since you know what the broadcasting station, the signal for it is 4 megahertz, you would want to change C so that it corresponds to that frequency, so that the peak of the resonance hits that frequency, and now you are in sync and you can listen to that station at best, basically. So C now, we have 78 times 10 to the negative 3. That's what the micro, 10 to the negative 6, that's what the micro stands for. Microhenry, that's a tiny, yeah, microhenry, times 2 pi times f, and f is 4 times 10 to the negative 10 to the power 6 squared. Okay, so this gives me, did I do a mistake in here somewhere?
I think L should be divided out, right?
Yep, yeah. Thank you very much. Yeah, you see, because I was getting a huge number for the capacitance, okay? because 10 to the power 6 squared and times 10 to the negative 6 is going to be 10 to the power 6. And I know the capacitance cannot be that big. Otherwise, we have a disaster. You know, if I need to build that capacitor, probably have to drag a truck in here to a truck to build a radio. Okay, so everything is inverted. C comes up and I have L in the denominator times that's the number squared. Okay, so let's do that now. So I have 10 to the power negative 6, and one of these 10 to the power 6s are gone, basically, and I will be left with only 10 to the power 6 in here, okay? And I will be left with 2 pi. Where is the 2 pi coming from? Where is this 4 coming from? Ah, 4 from the frequency. Okay, good. 2 pi times the frequency. Okay, so let me 1 over. So I don't really need to write the 10 to the power 6 because I know the answer is going to be in microfarads in here, whatever it is, and probably is going to be smaller. So I'm going to be left with 1 over, open parentheses. I have 78 times open parentheses because I want that number to be squared. I have 2 times pi times 4. And the whole thing is squared. This number is actually squared. And the whole thing is close the parentheses for the denominator. Oh man, it's even smaller than a micro. So it's 2 times 10 to the negative 5, 10 to the negative 7. So let me get rid of these 2 numbers in here. So it's extremely small, okay? So 10 to the negative 11 times 2, that's 10 to the negative 12. So it's going to be 20.3 actually, picofarad. Okay, extremely small. So that's how you change it. So that's how you change the dial. Now you're in tune. Your circuit is actually tuned for that 4 megahertz station. Okay, that is broadcasting 4 million hertz basically signal, which is the radio frequency, by the way. Okay. So we found the value of C. What RMS value of the current IRMS flows in that case? Okay, when we are at resonance, the impedance is equal to Z. Remember, it's equal to R squared plus LC or XL minus XC squared. But at the resonance, these two are equal to one another, and the difference between them is 0. So the impedance is equal to the R in this case, okay? And R is given to be 100 ohms. So we have that value. And all I have to do is just divide this EMF by basically R, and we're in business. Did I find the, no, I have to divide it by square root of 2 because this is the maximum basically EMF. Then I have to divide it by square root of 2 one more time, and that's it, times 100. So here is the IRMS is equal to VRMS divided by 2. Square root of 2, and divided by R in this situation. Okay. I'm sorry, VRMS divided by R. And VRMS is V naught divided by square root of 2 divided by R. So IRMS in this situation is going to be equal to 1 over R, which is 1 over 100, times V naught times square root of 2 in the denominator first, times V naught. V naught is in the entire thing in here, including the sign, by the way. That is the amplitude of the signal. So it's going to be 2 times E naught times, oh man, I don't have E naught, do I? I need to find E naught. They didn't give me E naught. I have A, I have N, and A is 0.1, N is 50, and 2 times 50 times 10 to the negative 1. So there's some cancellations in there. I need to find E naught. Since I have the intensity of the wave, what is it? It's 100 watts per meter squared. And we already found a way on how to find from the intensity on how to find basically the strength of the electric field. Here is the expression. They gave me the intensity. This is the speed of light. It's not the capacitance. Please don't confuse your C's also. So this is the speed of light. This is mu naught, which is constant. So I have to do now is find the electric field now. So the electric field first, which we needed for this expression, is equal to square root of 2 mu naught c, which is the speed of light times the intensity. Since they gave me the intensity, this is 2 times 4 pi 10 to the negative 7 times 3 times 10 to the power 8 and times 10 to the power 2. And 10 to the power 2, which is the intensity, and that is basically it. Okay, didn't we do this number before? I think we did. E naught. Let me see what this number was. It's the same thing in here. Previous problem. This also had 100 watts per meter squared for the laser beam. And this one also has 100 watts per meter squared. So all I have to do is just use the same value, 275 volt per meter in this expression, because I know if I did it correctly, so this should be 275 volt meter. So this number should be 275 now, without having to actually do the algebra, because we did it. Please verify these things. Don't rely on me, okay? So this thing in here is 275, 2 times 275. That's the strength of the electric field times A, and A is 0.1, 0.1 or 10 to the negative 1 times, what else do I have? N, which is 50. 2 times 50 divided by 100 are gone. That's easy. Okay. Don't forget the sign of Ka over 2. And you need K for this problem. K is 2 pi over lambda. And 2 pi divided by lambda. And lambda, if you remember the dispersion law, lambda f is equal to c. So from here, we're going to find lambda equals to c over f. They gave me the frequency. I have the speed of light. So this is c and this is f. So I need this number, and multiplied by Ka divided by 2 is going to be pi f a over c. And I already canceled the 2 from the numerator and the denominator. So this is pi times the frequency, which is 4 times 10 to the power 6, times the width, which is 10 centimeters, 0.1 meters, divided by 3 times 10 to the power 8. Again, cancel this, I have 10 to the power 2 in here. And when I bring this one, it's going to be 10 to the power 3. So it's going to be 4 pi divided by 3,000. Okay? 4 pi divided by 3,000. And that's a very tiny number. And I need the sign, by the way. So the sign of Ka over 2 is the sign of 4 pi over 3,000. Okay? This angle is so small. And it's in radians, by the way. This is in radians. So when you're calculating this thing, make sure your calculator switches to radians. Do not use degrees, okay? Because this number is actually in radians when you do it this way. Now, because this number is so tiny, 4 pi is what? Pi is 3 times 4 is 12. 12 divided by 3,000 is a very small number. If you do this Taylor series for the sine of x is equal to x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial and so on and so forth. This number is going to be extremely small compared to x because x cubed. So this number is basically 1 over 1,000. And 1 over 1,000 when you cube it is 1 over a billion. So we're making a correction of a millionth compared to this one. So that's why this number is roughly 4 pi over 3,000. Okay, end of the story. So I don't even need to punch it on a calculator. And if you don't trust me, just punch it on a calculator. Make sure your calculator is in radians and you should find the same answer. Okay, so having said that, now I have an expression for the intensity. So this number times 4 pi over 3,000. Now we are in business, okay? So we have 10 to the power 8. So we should, no, I'm sorry, what am I doing in here? Why is this here? This is actually wrong. It's going to be here. Here. This number needs to be replaced by 4 pi over 3000. That's what I'm trying to find, the IRMS. I have 275 divided by square root of 2 times 10 to the negative 1 times 4 pi divided by 3000. That's what I want to find for the current. So I have 275 times 0.1. I should have done this quickly. Times 4 pi divided by open parentheses square root of 2. And I have 3000 in front of it. Okay, I didn't make any mistake, and hopefully you guys are here to make sure I don't. The answer for the current is 8.1 milliamps, or 0.08, no, 81 milliamps, 81.4 milliamps. Okay, let me write it down how the calculator wrote it. 0.08145, so I'm going to round it to 5 amps. Okay, so 81.5 milliamps. And this is expected, okay? You can't have a strong signal in there. You can't have a strong current in there, okay? So this is a typical number. Okay. Oh, did I forget? Yeah, I forgot big time. I'm sorry. No, that's good. I thought I forgot to divide by the resistance, which is 100. And I already took care of that when I multiplied the 2 by 50, the number of turns, and there was a 2 inherently in the formula. So 2 times 50 divided by 100, that took care of that 100 in the denominator for the resistance. So everything should be well, okay? Does this make sense to you? It's a long problem. It's not an easy problem, though. A couple of you guys left. I know that's the reason why we did it this way.
I think I'm just a little bit confused about one part. For when you are doing the IRMS, and so what exactly did you replace for V naught?
The entire coefficient of the wave here. Where is the signal? Where is the? This is your power source now. This is the EMF. This is the battery, if you wish. Okay. This is its voltage. This is its V max, V naught. Correct?
Yeah.
And
okay.
this is its frequency omega. Okay. So this looks like it's a power source that has a V naught equals to everything in here, 2 E naught AN times sine of KA over 2. That is V naught. And an omega, that is the coefficient of the time in here. This is the power source that is coming from the wall. So if I want to find the IRMS, technically, I should divide the VRMS by Z. But I am at resonance. At resonance, Z is equal to R. And VRMS is the same as V naught divided by square root of 2. And V naught is the entire expression in there. The coefficient of whatever the trig function in here. It happened to be a sine, so be it. It's a sine. If it was a cosine, so be it. It's a cosine. It doesn't matter. The coefficient in absolute value, we really don't care also because this is the maximum voltage. Okay, it's 2 E naught. The problem is we don't have E naught. They didn't give us E naught. They gave us the intensity of the wave. So we needed E naught. For E naught, we had to use an expression that we used several times before, and it's this one, because they gave us the intensity of the wave. We know the speed of light, we know mu naught, so we can find the electric field now, the maximum of the electric field. We plug it into this expression, and now we know everything about the problem. It's not an easy problem, I must admit. I'm hoping that you guys understand it, though, because this is a practical problem of what you do trying to build an antenna.
Definitely makes more sense, though. Thank you.
Okay, no problem. Okay, guys, so let's recap because it's a nice problem to work with, okay? So what they gave us in here, let's go back in here. They gave us N turns in here, and they gave us the inductance in here, L, for the circuit. And we have an R and we have a C. So the point being in here, a wave that is traveling in the z direction hits this antenna. And as it does, it's going to have an electric field and a magnetic field. The magnetic field in here component is going to induce a current in this RLC circuit, basically. And how is it going to do it? By having an EMF in here that is time dependent, because the flux of the magnetic field that is in the x direction depends on time. If I take the derivative of the flux with respect to time, I'm going to find the EMF. And the EMF needs to be in resonance in here for me to really have a strong signal. Remember, the characteristic of the resonance is this peak in here. So this is omega naught of the circuit, which is 1 over s square root of LC, must match this frequency of the signal for me to really have the resonance, okay? And we know the frequency of this broadcasting station, which is 4 megahertz. So we needed to really tune our C in such a way that we are at resonance. And if we are at resonance, in this case, the current I naught is just V naught over Z, but Z now is equal to R at resonance, okay? This is from chapter 31. So that's basically in a nutshell, but they didn't want us to find the I naught. They want us to find IRMS because this ammeter really does not really read the maximum amplitude. It reads just the root mean square, the effective current, okay? In other words, the current is fluctuating so much, because remember, 4 megahertz just happens 4 million times every second. So what matters at the end is just the effective value, which is, so at the end is just an RMS, a root mean square that is basically going to be the average, basically, okay? So that is really what matters at the end of this circuit in here. So this is why they want this one. So you have to divide everybody by square root of 2. So you divide this one by square root of 2, you divide this one by square root of 2, and this becomes the IRMS. And that's why that square root of 2 is needed in here. So now we have that. So we needed to find the flux, which is the area times the magnetic field. But the magnetic field depends on Z. So we need to take a strip of area and integrate throughout the entire side by side from negative A over 2 to positive A over 2. Because the magnetic field depends only how far we are up and down. It doesn't depend left or right. It doesn't depend on Y. It depends only on Z through the cosine of KZ minus omega T. So because of that, then we had to do an integration in order to find the entire flux. As we should, it should depend on T. As the flux at the end, we took care of this trig stuff and played around with things. And the main thing that turned out in here, the flux has this cosine of omega T in it. If I take the derivative of the cosine, it's a negative, but don't forget Faraday-Lenz law has a negative already in it. So that takes care of the negative sign. But don't even blink twice about this issue. It's not a problem. In other words, you could have sent a signal from the other side and the sign becomes negative. So be it. Just shift everything by 180 degrees or something to fix things. Or what matters is the amplitude. In other words, is the current really going this way, or is it going that way? It doesn't matter. It's going to oscillate, okay? Sometimes going back and forth. And then at the end, what matters is just the amplitude of the current. So the sign in here, the fact that we had it positive is irrelevant. It could have been negative. What matters in here, this coefficient of the trig function. That is the amplitude of the current that you ended up with, including this sine Ka over 2, which is a critical. It could lead us basically to no signal at all, even though you are at resonance. Because if Ka over 2 is exactly a multiple of pi, then the sign of a multiple of pi is going to be 0. So in this case, it doesn't matter. The EMF will be 0. There will be no current. Okay? There will be no current. So if you make your geometry slightly bigger or slightly less, that could impact your signal. Okay? That could impact it. As a matter of fact, you want probably to, if that's the only station you're worried about, then you could probably I make this value in here 1, make it at most, which is 1. So in this case, this whole thing becomes at its best in here. Okay. So that is in a nutshell, including the n, by the way, which I forgot. I'm sorry about that. Okay. So that is actually the whole problem in here. It's not an easy problem. But at the end, you see so many things come together in here in this problem, including Taylor series. Okay. And the current as expected should not be too high. If you find an amp in here, that's too much of a current actually. 2 amps is a huge current. 50 amps is disastrous. When the phone doesn't have 50 amps in it. You don't want that much current in the circuit. Okay. Problem 4. Problem 4 was an exam in the past, so you probably would want to understand that problem also. So problem 4 says the company where you work as, so problem 4, I call it 4 because it's 46, problem 46, okay? The company where you work has obtained and stored 5 lasers in a supply room. You have been asked to determine the intensity of the electromagnetic radiation produced by each laser. The lasers are marked with specifications, but unfortunately, different information is given for each laser. So laser A, so I'm going to put them A, laser A. They tell you specific has the power is 2.6 watts. Okay. And cylindrical beam, the diameter D is 2.6 millimeter. This is the diameter of the beam. Okay. B, they gave you for B, the electric field, the amplitude of the electric field is 480 volt per meter. For laser C, they gave it's labeled as the magnetic field, the intensity of the magnetic field is 8.7 microtesla. Okay, so each one of them, they give you a different value for it. D, laser D, they give you a cylindrical beam, diameter D is 1.8 millimeter. In other words, it's narrower than the other one, very narrow, okay? And force on totally reflecting surface, basically the force on a reflecting surface, to being equal to 6 times 10 to the negative 8 newtons, okay? What else? And laser E has an average energy density, where is it? ABCDE. U bar is equal to 3 times 10 to the negative 7 joules per cubic meter. What else do they give us? Calculate the intensity for each laser and rank the lasers in order of increasing intensity, assuming that the laser beams have uniform intensity distributions over their cross sections. So find the intensities, basically. The first one is easy. The intensity of this guy should be P over pi times D over 2 squared. Okay, the same argument that we made earlier and Martin asked about it. It's pi r squared, and r in this case, they didn't give me r, it's just this. So this is easy. So we're going to find a number in here, okay? I'm not going to do all of them, but I hope that you guys can finish this thing here. This one, they gave me E naught, and I know how the intensity is related to E naught. Actually, you can use this expression. I is equal to E naught over 2 mu naught C, where mu naught is just a constant and C is another constant. So I, in this case, is equal to E naught squared divided by 2 mu naught times C. C is the speed of light, and mu naught is 4 pi 10 to the negative 7. So I can find I in here. Here, they give me B. Well, I can find E naught by multiplying it by C. So CB naught. So I'm going to square this C in the squared and C cancels. So I is going to be CB naught squared over 2 mu naught. So it's the same expression in here because B naught and C naught and E naught are related through C in here. So now I have an I in here, an I in here, and an I in here. So we need to find this I now. Remember the force. Let me go back into the lecture where we found the force, which is dP over dt. The force is P over C or AS over C, however you want to write it. And S on average, when I average this quantity, is going to be I. So it's AI over C. So let's go back into this problem. AI over C. So it's A. So this is D, okay? It's A. And A is pi times D over 2 squared times times the, oh no, I need to solve this equation. Let me go back into this expression here. Since I have F now, I need to find I. So I is equal to C times F divided by A. So that is the expression I need to use in here. So I is the speed of light times the force. So let me clear this thing in here. Oh man, I can't delete everything at once. Okay, I think I got it now. So I in this case is equal to C times F divided by A, and A in this case is pi times D over 2 squared. And F is this force in here, okay? And C is the speed of light. So we have everything. And now we have the last expression in here, and we know that there is a relationship between U and actually I. Actually, U is equal to I in this case. Okay. Where is the expression here? Sorry, there is a C between them. So I is equal to CRU, okay? This one, I, because this is the average. So in the I, the intensity will be just the speed of light times U bar. Does everybody see that this is doable? This problem is doable. Once you find the I's, you're going to rank them from the highest to lowest. You guys see that this is doable based on the lecture? Okay, very good. So we're going to skip through this problem. Hopefully you guys can finish it for me. Problem 5. How are we doing on time? We're almost 2 hours in. How is everybody feeling? Should we continue or and post the other two?
Couple more.
Sorry?
I could do like 1 or 2 more, yeah.
Okay. Okay, so let's get at least one more. Okay, the solar sailing. That's problem 44. Problem 44. Problem, by the way, 44 and problem 37 are not too different from one another, okay? So let me get this problem 44, which is an important problem. So NASA is giving serious consideration to the concept of solar sailing. Problem 44. A solar sail craft uses a large, low-mass sail and the energy and momentum of the sunlight for propulsion. So the sun is pushing it basically with radiation. Should the sail be absorbing or reflecting? Of course, it has to be reflecting, because if it's absorbing, then it's just 1. If it's reflecting, it's 2. So if you guys remember, the pressure from the lecture has a 2 in it. Where is the expression here? For the reflecting, and 1. So the absorbing material, the pressure is going to be S over C, and for the reflecting material, it's going to be 2S over C. So it's going to be better to have it reflecting. So because as the wave bounces back, so it's going to move further, faster. So that's the first question, which is easy to answer from the lecture. B, the total power output of the sun is 3.9 times 10 to the power 26 watts. How large a sail is necessary to propel a 10,000 kilogram spacecraft against the gravitational force of the sun? Express your answer in square kilometers. Here is the problem. You have a 10,000 kilogram sail ship. Here is basically a ship, 10,000 kilograms. And you would want it to sail due to the radiation. So the radiation is pushing it with a force in here, but the gravity is pulling it toward the sun. So this is the mass of the sail times the mass of the sun divided by the distance squared between it and the sun and times g. So this force of radiation must be at least equal to that number for you to have it accelerated. If it's not enough, then you cannot overcome the force of gravity due to the Earth. So let's find this force of radiation. Remember the force of radiation in this case from the lecture again. We just wrote it actually. The force of radiation, we just wrote it in here. The force is equal to did I have this wrong? Yeah, this is the size of the sail that you need. Okay. I times the size divided by c. So that is the expression that we need in here. So this is equal to the intensity, okay, of the radiation times the size of the sail, which is the area A. So IA, we want it in square kilometers, basically. That's what they want the answer to. Divided by C, divided by the speed of light. So this must match. The radiation of the sun started way back at the sun in here, and it spread throughout this entire radius R. So it's over a sphere whose radius is R. So the area of the sphere in here must be 4 pi r squared. So here is the equations that need to match. From one side, we have the force of gravity. This is the mass of the sail. This is the mass of the sun. And this is r squared. This must match the area of the sail, which is coming from here, times divided by c, the speed of light, times this one. And this is the power radiated from the sun divided by 4 pi r squared, where the r squared is the same as the r squared in here. This is the distance squared between it and the sun, and this is the area of the sphere where the ship is at this point. And the area of the sphere is 4 pi r squared. So the r squared cancels the r squared. And from here, we know the power, it's 4 times 10 to the power 26, basically 3.9 if you like, 10 to the power 26 watts, okay? The area is what we want. This is how big the sail need to be in order for it to propel it. C is the speed of light. The mass is 10,000 kilograms. The mass of the sun is 10 to the power, did they give you that number? Or we have to Google it? I don't want to give you a wrong number. It's 2 times 10 to the power 30 kilograms, I believe. 1.9 or something like that. Mass of the sun. It's 2 times 10 to the 1.989. 10 to the power 30. So this is 1.989 times 10 to the power 30 kilograms. 30 kilograms. And then G is 6.67 times 10 to the negative 11. So we have all of the numbers in here, and from here we should be able to find this area. So don't forget, I have in here 10 to the power 26, 10 to the power 34, 10 to the negative 11, and the speed of light, don't forget it's c. So the area A must be equal to G times M of the sun divided by P, the power of the sun, and times the speed of light c. So that is basically in a nutshell what these things are. So let's plug in the numbers. We have 6.67 times 10 to the negative 11. We have the mass of the object is 10 to the power 4, and the Earth, I'm going to put 2 if you guys don't mind, okay? 10 to the power 30 times 3 times 10 to the power 8 divided by 3.9, I could have put it 4, times 10 to the power 26. Let's get rid of the powers, okay? 10 to the power 26 and 10 to the power 30 gives me 4 in here. So 4 and 4, that's 8, and 8, 16, and negative 11, that is power 5, okay? So this is 10 to the power 5. Everything, all the powers are gone, okay? All I'm left with is to do the algebra here. I have 2 times 3, which is 4, which is 6, I'm sorry, times 6.67 divided by 4, actually, that's what I'm thinking about in here all along, 3.9, times 10 to the power 5 square meters. Wow, that's a big number. Does this make sense? Huh. Please verify these numbers, because it looks so big for me. But it's a big number. It's supposed to be a big number. Did I put it in? Oh, in meters. I'm sorry, meters squared. Because everything is in SI. This is in meters squared per second squared. So this is, everything is in SI. Everything in here. This is in kilogram. This is in kilogram. This is in SI. Everybody's in SI. This is in watts. So thank God. I was thinking for a second that I was going to have a big. So this is meter squared, okay? So yeah, it's still big, but not that big, okay? Not 10 to the power 5 kilometer squared, because they want the answer in kilometer squared, basically. So a kilometer is 10 to the power 3. When you square it, it's going to be 10 to the power 6. So this 10 to the power 5 is gone with the 10 to the power 6. So I'm going to be left with 10 to the negative 1. So in other words, 6 times 6.67 divided by 3.9 square meters divided by 10. So what is my calculator in here? So it's going to be 6 times 6.67 divided by, open parentheses, or no, I need to open parentheses, 39 there directly. So it's 1.026 square kilometer. That's still a huge sail. That is a big sail. It's, I mean, from here to Walmart. I don't know where you are right now, but it's a huge sail. Okay? It's not a small one. In order for you to overcome the force of gravity, I mean, it's still, how many, 1 kilometer squared? It's basically kilometer by kilometer in size. 1 kilometer by 1 kilometer. City block by city block, basically. From a city block to another city block. So you have a bunch of stores in here, a bunch of stores in there. Does this problem make sense to you? Okay, it's easy enough because it has a lot of the things that we have again and again and again and again and again. A lot of these problems are repetitions of the same thing. If you really pay attention to them, the only problem that was a bit hard is the problem with the antenna. Okay, the others are repetition of the same thing. So again, what's the next question? First of all, how large is this case? So we found it. Express your answer in square kilometers, because if we left it in square meters, it gives you 10 to the power 5 square meters, and 10 to the power square meters, I mean 100,000 square meters doesn't really tell you, doesn't give you the visual that it's about city block, basically, in say in size, which is a huge one. Okay. Part C, what is part A? Part A is already, we answered it. Now, which one? It has to be reflecting. Oh, did I forget the 2 in it? Maybe the 2 will make a difference. Yeah, there is a 2 in the expression. So it's slightly less than what it is, okay? So fix the problem. So if this was absorbing, it's going to be this number, okay? So it's going to be slightly less, actually. That's good, okay? explain why your answer to part B is independent of the distance from the sun. It's independent from the distance of the sun because the force of gravity is inversely proportional to distance squared, and the intensity of the radiation is actually propagating through a sphere whose radius is r. Therefore, it's a 4 pi r squared. The r squared cancels the r squared. So this doesn't matter how far you are from the sun. You need that huge sail. If you are close by or far away, you need to overcome the force of gravity. The force of gravity is inversely proportional to r. Okay. I hope you guys, I know it's 4 o'clock, it's 2 hours already. So this is enough problems. To problem 37 is similar. For the problem 37, basically what you have, we have on one side a perfectly reflecting surface and on the other side the absorbing surface, and the two spin. So you find the force on one, which has the 2 in it, and the force on the other, which has 1 in it. So now there is an imbalance of the forces, so this starts to spin. You find the force times distance, that's the torque of this force. You find the torque of the other one, which is force times distance, and both of them are facing the same radiation. Okay. There is actually a toy that is actually in the physics lab where we have to, it starts to spin when it is exposed to the radiation. That is exactly the principle behind it, because one side is perfectly reflecting, so the radiation hits it, bounces off, and the other one is absorbed, so there is less force on one side and twice as much force. So now you can find the torque. From here, since you're given I, the moment of inertia, since you have the masses, you can find the angular frequency. It's going to be very angular frequency. You can find the angular acceleration. It's going to be a very tiny number. So that's it, problem 37. And that problem is one of the problems I suggested we should do. Problems 51 and 52 are actually for your general education. They are not part of the exam. Problems 51 and 52, so that you know. I mean, they're going to be critical for physics 4D if you're going to take physics 4D. Because once you take physics 4D, the model of the hydrogen atom immediately faces tremendous problem in terms of its proposal that, hey, the electrons are moving around the nucleus. And since the electrons are spinning, they must be under an acceleration. And the accelerating charge will radiate energy according to the formula that is given in problem 51. Problem 51 gives you q squared a squared, where a is the acceleration, divided by 6 pi epsilon naught c cubed. So this one would radiate energy. So if you do plug in the numbers for the electron, you will find that the electron will immediately fall to the nucleus. So that is the idea from it. So I'm hoping that you guys go through those two problems, not in part for preparation for this exam, but more for the physics 4D. As an argument for physics 4D, why this physics is no good and it has to be revised. And we did not derive the expression that is given in 3251. As a matter of fact, derivation is very, very, very hard to do on this level. You have to get into upper division courses in physics to really see how it's derived. So at this point, we're going to probably skip problems 51 and 52, but I was hoping that we do them in practice. So problem 46, I left it for you guys to finish it. Problem 51, we discussed it. Problem 42, we discussed it and we killed it. I hope that it's good. Problems 22 and 23, they're done for you guys. So that especially problem 22 is more important than problem 23, honestly, because 22 will summarize everything that we did in it. I mean, it's a simple problem, but it has a lot of the things that are in there. The biggest thing that is coming from these problems is I and S bar is the same thing. The average pointing vector and the intensity is the same. And then go back through the formulas and find everything. So I'm going to skip problems 35. 35 is similar to the problem we just did on solar sailing, okay? Except that it's on top of the surface of the sun and halfway midway the surface of the sun. And the argument from that problem is that basically the solar radiation, I mean the pressure, radiation pressure is negligible compared to the gas pressure. Okay, so that's why the thermodynamics of the sun is more important than the actually EM waves and how much pressure they exert and things like that. Okay, so for those problems, so I'm gonna skip these two problems for right now. Does this make sense to you guys? Good. Because I feel some of you already have left, at least a couple who have left. And we have covered 2 hours, a little over 2 hours right now. Do you want to continue, guys, or is this good enough?
I think I'm good here.
Okay, good. How about everybody else?
I think I'm good.
Okay, some other people are putting stuff in the
This
chat.
is recorded, right?
This is recorded, yes, and it's going to be posted later on Canvas. So please go through these problems, understand them, go through all of the problems we have done them. And if you have any questions, please do not hesitate, ask them outside of the class. And as I said before, if the question turned out to be of importance to everybody else, I'll share it with everybody else after asking your permission, okay? And if it's just related to you only, then I'm not gonna record it, okay? It was very nice to have you guys in my class today. Actually, I was excited to go and look at the lunar eclipse. I couldn't, I left early in the morning, actually. I took my car and drove all the way to India to see if there is a better weather. Like a nut, basically, crazy. In there with my binoculars and camera, and there was clouds everywhere, so I couldn't see it. So I missed on it today. There is an event that is gonna happen in October, and that is the James Webb is going to be deployed. Let me remove this image sharing in here. The James Webb is going to be deployed. So I'm hoping that you guys join us in the STEM Center during that event, which is a big deal. Probably I will not be meeting with you again at all until, until we see each other during the exam, the final exam on campus. So I wish you the best of luck. And if you ever need the stuff later on after class, during class or anything like that, you have my contact info. Sounds good?
Sounds good. Thank you so much for everything, Professor.
Thank you, guys.
Thank you.
Thank you, guys. Gotta stop the recording.
Question.
Yes,
It's regarding the homework.
yes. The homework, I actually stopped from assigning new ones because honestly, the way that Pearson is putting them, and sometimes they were not to my taste, honestly, and I thought that they are not going to be helpful. So I stopped at somewhere a long time ago for, I think we have several chapters, but it's important to do those ones so that they will be part of your grade. So if you didn't do them, and if you think that the time has expired, please let me know to reopen them for you again. Make sense?
Yes.
Yeah, I got it.
Okay, very good.
And is
So-
homework a big part of our grade, or is it kind of like a small one?
Should be on Canvas, okay? I don't know how much is it, 20% or something, or 10%, 15%? I really don't have the exact number right now on top of my head. It should be in the syllabus on, let me look at it quickly in here. Is it 20?
Yeah.
If it is 20, it is 20. Yeah, the homework is 20%, so please take, very important. The exams are 40%, labs 25%, those are 5%. Don't forget you have a couple of quizzes already. And that's our still do, of course. And you have the participation rate 10%.
Professor, just a question. When is everything is due? Like the last chance?
For the things that have already been done, and they should be on Canvas where it tells you that they are due. If you received a mark for it, that's it, they're done. If you did not receive a mark for it, a grade for it, they're still basically until the time for me to come and grade them, okay? I plan on grading this weekend, so especially the stuff that was done a long time ago, please take care of them before that, okay? That's of an urgency. If you look at the question that Rami asked earlier about the weight of things, don't forget the exams and the final. They're very, very important stuff. So if I have a lot of things that are due and I did not do them, I try to do as much as I can, but don't forget to prepare for these exams because they have tremendous weight on your. The labs also, they have a huge weight, 25%, although the labs, because you have so many of them, at the end, each and every one of those labs becomes less and less basically effect on overall grade. But the exams, since in this term we only have 3 of them, really, we have a midterm and another midterm and a final. So they carry with each and every one of them tremendous amount of weight. Okay? So if you're struggling with anything, and you think that you're falling behind on your assignments and things like that, please reach out to me. so that we can come up with a plan, okay? And we're gonna do it on a one-to-one basis. We cannot do it on a classroom environment.
Okay, thank you, Professor.
Thank you, Professor.
Thank you, guys.
Thank
All right,
you.
see you soon.
Bye.
Thank you, bye. Let me stop recording.